Okay, I'm Richard Friberg, and this is from chapter 3 in my microeconomics textbook. And we'll be looking at the slope of an isoquant and why we can think of it as a ratio of marginal products. Okay, so let's start with looking at an isoquant for imperfect substitutes. So we're using, we're thinking of, say, bread. You know, how much bread can be produced? Well, it depends on the input set we're using. We're thinking of two inputs, capital, so machines, ovens, etc., and labor, number of workers who are working on this. Okay, so there's something like this. There are a large number of different isoquants that would be above this, but for clarity, we just focus on one. We want to see how can we trade off capital against labor, one input against the other, and how does that ratio depend on how we're able to trade off? How does it depend on where we are? Okay. So let's look here. So what are we looking at? Well, we can think our starting point is a production function, right? So how much output, how many units of bread we're producing, and how that depends on how much capital we're using and how much labor we're using. So before we go anywhere here, let us introduce some notation. So D, we use that to denote a change. So just a small change in some variable, could be capital, labor, and or quantities produced. We also use the following, delta, lowercase delta, the Greek letter delta, like this. So delta Q of K and L over delta L, for instance. What's that? That's a partial derivative, in this case of the function, with respect to L. Okay, so we're changing L, keeping everything else constant, and seeing how the quantities produced respond. Okay, so this is the partial derivative of that. Okay. Good. So an example would be if the production function is given by L squared times K squared, the marginal product of labor here, which is another way of saying the partial derivative, would be simply differentiating this. So differentiating this expression with respect to L, so the 2 comes down, L to the power of 2 minus 1 is just L, and K2 or K squared is kept constant. So we're saying, we're seeing in the change as we change L and keep everything else constant. Okay, so this would be the marginal product, the partial derivative of that. Okay. So those were just preliminaries. What we instead want to do, we want to engage in what we call a total differentiation of the production function. So we totally differentiate the production function. We let everything change, see what that can teach us. Okay, so D said was changed. So let's see, changing quantity here. How can we decompose that? Well, we can think of the effect of changes in capital and how that affects output. So changing capital, change capital, and see how does that change in capital affect the produced quantity. So the marginal product of capital, if you wish, the partial derivative of the production function with respect to capital. So that's one part. We're looking, what happens if we're changing capital, but capital is only one of two production factors of production. The other is labor. What happens if we're also changing labor? Like that. Okay. So the total change in quantity produced equals the change in capital times the marginal product of capital plus the change in labor times the marginal product of labor. We're looking at small changes here. What do we know about the change in quantity if we're moving along the isoquant? Well, iso being Old Greek for the same, we know that this change is zero, right? So we're not changing, we're keeping quantities constant. That's the whole point of an isoquant, where this is 100 loaves of bread, you know, producing 100 loaves of bread here, we're producing 100 loaves of bread here, we're producing 100 loaves of bread here. We're keeping quantity constant. Okay, so we can just reshuffle here, noting that that is zero. So we have here delta Q KL over delta K. K, it's a minus since we're moving it to the other side of the border here. KL delta L, the marginal product of labor, times DL, the change in labor. Okay, so we can then divide through by DL, and we can divide through by the marginal product of capital here. So dQ KL dK, which means that this is, we can cut that out and move the in like this. So what is this saying? Well, this is the slope, right? This dk, d over dl, what we sometimes call the marginal rate of technical substitution, MRTS. This is equal to what? The marginal product of labor, MPL, over the marginal product of capital, MPK. Okay? So that's saying that the slope here is equal to the absolute value of the slope, rather, is MPL over MPK. Okay, so that's saying in a point like this, it's super automated. This is like a bakery in Japan. Yes, you know, have lots of capital, lots of machinery, little people, or few people rather. And down here we have, you know, somewhere else where there's little capital, lots of people milling around. In a point like this, where there's a lot of capital per person, you know, that person will have a high marginal product relative to the marginal product of capital. Okay, so a worker they're sitting with supervising machinery for, I don't know, hundreds of thousands of dollars, will have a high marginal product relative to a case, say down here, where there's many people milling around, limited set of ovens and machinery equipment, and having relatively low marginal product of labor, in particular set in relation to capital. Okay, so this is the intuition and the background to why the slope of the isoquant, the marginal rate of technical substitution, is given by the ratio of the marginal products.